Hello everyone, welcome to Spectre Education. I am Dr. Rajesh Panja, and this is physics for physics for engineering students, engineering students, right? And this course is basically for first year students because all of you know that either in first semester or second semester physics is a mandatory subject for any branch of engineering students, and this may be for CSE, ECE, mechanical engineering, civil, including biotechnology, right? And under physics there are different topics like the quantum mechanics, acoustics, solid state physics, statistical mechanics. So if you follow this lecture series, you can find that for each and every topic you will find several videos, and through these videos you can prepare yourself for your exam. So let's start with a very important chapter, vector calculus. And under vector calculus today I'll discuss about this topic, the gradient of a scalar field. If you observe carefully, you will find there are several new terms like the gradient, scalar field, etc. So based on our today's discussion, this is you can think this is the content. So first we will discuss about what do you mean by the scalar field or function. Second, we will learn what is the physical meaning of the gradient of a scalar field. Then we'll solve several numericals, and we'll learn how to solve these problems within 30 seconds. And if time permits, then in this lecture we'll also cover two different applications of the gradient of a scalar field. So let's start with what do you mean by the scalar field. I believe that you all know about the scalar quantities, right? What is the scalar quantity? You all know that these are the physical quantities having magnitudes only, and we don't need to consider their directions, right? These are the scalar quantities. So as for examples, you can think about the mass, you can think about the temperature of an object or a room, you can think the volume, you may also think about the length, pressure. There are lots of examples about the scalar quantities, and I believe that you all familiar with the scalar quantities from the school days. But what do you mean by the scalar fields? So for that, let's take an example. I think you can just see this beautiful picture, the beautiful picture of a beautiful place. And if you observe that, you can find that maybe there are temperatures are different in different positions within this place. Maybe at that point we can think this is a very cold region. Let's say this is the 50 degrees centigrade, and if you move that point, let's say this is the position A to position B, maybe the temperature is a little bit higher. Let's say this is 18 degrees centigrade, and if you move here the position C, maybe it is 22 degrees centigrade, and so on. So if you move throughout this space, at each and every point you will get certain values of temperature, right? So in other words, we can think that temperature is continuously spread over this place, because there will be no such a point where you will not get the values of temperature. So we can think that temperature is continuously spread over this place. What is the temperature? Temperature is a scalar quantity, right? So when any scalar quantity is continuously spread over a place or in a space, then this creates a scalar field. For example, the temperature. So temperature at each and every point, if you move from A to point B to point C and so on, so for different points, obviously you will get some values of temperature. So we can think the temperature is continuously spread over this place. So right now temperature is a temperature field, and this field can also be called as a function. Why? Because you can see that temperature is a function of position xyz, because when you change from position A to B, you will get the different temperature. When you get change from B to C, you will get another values of temperature. So with changing the position, you will get the different values, maybe the certain point the same values. That means you are getting the values of temperature. So in mathematically we can write temperature is a function of position. and this is also known as the temperature field. So in a word, we can see what is the difference between the scalar quantity and scalar field. When we are talking about the scalar quantity, that means we are considering a single value for a particular position. But when we are talking about the scalar field, then we are talking about the each and every values of that scalar quantity in this space. Okay, so this is the concept of scalar field. So let's just observe what is written here about the scalar field. So consider a scalar quantity, for example a temperature, and if this quantity is continuous in a region of space, then the collection of all the scalar values creates a field. And as we have seen, that scalar field is also known as the scalar function, right? So now, what do you mean by the gradient of a field? Although you may think that gradient is a new word to you, but it is not new to you. I believe that you all familiar with the computer, and you are much more familiar than me about the computer, and there you have found out one term which is known as the color gradient, right? Color gradient. What do you mean by the color gradient? You just observe this picture and you will find at the bottom the color is a little bit light, and if you move from bottom to upward direction, the darkness of the color is increasing, right? So from the bottom to the top, the color is changing from the light to the dark. What is it called? It is nothing but the color gradient. What is the gradient? Gradient basically indicates the direction. It basically indicates the direction along which this color is changing from light to the dark. So gradient is associated with the direction. So keep in mind this concept and try to use here. What is the gradient of a scalar field? For example, let's take a scalar field. Let's say the temperature field. Temperature field, right? Temperature is a function of XYZ. It is nothing but the temperature. So what do you mean by the gradient of this temperature field? What is the meaning of that one? Just correlate with this color gradient. Gradient of a color means it is the direction, it indicates the direction along which color is changing its lower value to the higher value. Similarly, gradient of a temperature, we can say it gives us some information about the direction along which temperature is changing from the low to high value. We can think accordingly, right? Just comparing with this meaning of the color gradient. Okay, so not only gradient indicates the direction from low to high, but it is much more than that. We will explain shortly. So let's take an example. The same place you have just found out in the previous slide. Let's say this is the cold region, and somehow you are here and think that this is about the 15 degrees centigrade, but you need some warm. You want to move away from this cold region to get some high temperature. So along which direction you should move, by which you can get the increase of temperature. So there are several directions. You may choose this path, you may choose that one, you may choose this one. So there are infinitely different number of ways you can find and you can move along that direction. But among all these paths, there might be a path along which if you move, you will get rapid change of temperature. And you need that one because you are suffering from cold here. So you need the direction along which the temperature is changing rapidly, right? So if you choose manually, then it is very difficult to find out. It's not it. But gradient is a very powerful tool. In this position, then let's say this position is A. In this position, if you just take the gradient of this temperature field, it immediately gives you a direction along which the temperature is changing in a maximum way, or you can see rapidly. So gradient is so powerful. If you just apply this on a scalar field, it immediately gives you the direction along which the scalar field is increasing in a maximum sense. Okay, so here you can see that the gradient of temperature points the direction. It basically gives you a direction of maximum increase of that function. That means the maximum increase of the temperature. So this is the physical meaning of the gradient of a scalar field. So if it is asked in your exam, what do you mean by the gradient of a scalar field, or what is the physical significance of the gradient of a scalar field? The answer should be the gradient of a scalar field gives you a direction along which there is a maximum increase of that scalar field. So that much. Okay. Okay. So now what is the mathematical representation of the gradient of a scalar field? That means if I say that the gradient of temperature field, how to write mathematically? So it is written in this way, that gradient of a temperature field, it is written as in this way. So the whole term is nothing but gradient of temperature, or you can say temperature, right? And the first symbol, this is known as nabla. What is it? Nabla. It is known as mathematically, it is so nabla is basically vector differential operator. Why is it called so? So because the expression of nabla, it is very important. Sometimes it is directly asked, what is the expression of nabla? Nabla is I cap del del x plus j cap del del y plus k cap del z. Okay, so why it is vector? Because there are I cap, j cap, k cap. Differential, because there are del del x, del del y and del del z. And why is it called the operator? Because it operates on a scalar field or scalar function. And what is the physical meaning? So gradient of t, if it is written here in this way, it physically represents the direction along which t is changing or t is increasing rapidly. Okay, this is the physical meaning, right? Okay, so let's see how to solve any problem regarding the gradient. So let's take the first problem. How to solve that one, we will learn, right? And if you learn properly and carefully, you can solve any problem regarding the gradient within 30 seconds. So here one scalar field or function is given, that phi is equal to 2x z to the power 4 minus x square y. You have to find out the gradient of phi at the point 2, minus 2, minus 1, right? It is asked in this. So how to solve that one? It is very simple. Just follow this one. So gradient of phi, you have to write the first expression of the nabla, that is I cap del del x plus j cap del del y plus k cap del del z, and side by side you have to write the expression of the given function, that is 2x z to the power 4 minus x square y. So we can write this in explicit form, that is I cap. First this one will operate on this whole term, I cap del del x will operate on 2x z to the power 4 minus x square y plus j cap del del y. This is 2x z to the power 4 minus x square y plus k cap del del z, the same function 2x z to the 4 plus x y. Now there we need the knowledge of partial differentiation. But don't worry, if you don't know about the partial differentiation, or you have just forgot how to solve this partial differentiation problem, so here we'll also learn how to operate these partial differentials over these functions, right? So let's I cap. So del x, when this operate on the first term, always remember that del x will only operate on, so will only operate on x term. It will only operate x term, and rest of the term will remain as it is. If there are x term, then it rescue the other terms. Okay, so del x will just operate on the x. So del x of x, you all know what is this. This is nothing but the ordinary differentials. So del x is equal to 1. So it is 2 and z to the power 4 as it is. Del x of x is 1 minus, so in the next term del x will operate on the x square, y remains as it is. So first write the y, and del x of x square, it is 2x. Okay, now j cap del y. So del y will only operate on the y term. So in the first term, if there is no y term, then this del y makes this one 0. Nobody can rescue them. Okay, so del y of the first term gives you 0 because there is no y term. So minus, but in the second term, when del y operate on this x square y, there is a y term. So y rescue this x square, so x square remains as it is, and del y of y is equal to 1. Okay, plus a cap del z. So when del z operate on the first term, yes, there is a z term, so 2x will be as it is, and del z of z to the power 4 gives you 4 z cube minus, but there is no z term. When del z operates on this term, it gives you 0. Okay, so just simplify these ones. You will get that is 2 z to the power 4 minus 2xy cap minus x square cap, and plus, sorry, there will be no del z term. So this gives you 8x z cube, right? So what is it? It's gradient of phi. But you have to find out gradient of phi at that point. That means x is equal to 2, y is equal to minus 2, and z is equal to minus 1. Just put these values, 2 plus 2 and minus 1. You will get the result. So 2 into minus 1 to the power 4, that means 1, minus 2 into x is equal to 2 and y is equal to minus 2, I cap x square, that means 4 a cap plus 8 2 to zq means 1. So final result, solve this one, simple arithmetic, and you can get the. Okay, so let's take another example. This is also very simple one. So you have to find out the gradient of r at the point 1 minus. Okay, so gradient of r means, first write down the expression for nabla, I cap del x plus j cap y z, and then write down the expression given xy square plus yz cube, right? So now perform this partial differentiation. So I cap, I will now move directly, right? So del x will operate on this whole term. So when del x is operating on the first term, it will only operate on the x, and y square remains as it is, y square into 1. Del x of x is 1 plus yz cube. There is no x term. Remember that. So if there is no x term, when del x operates on this term, it makes them plus j cap. Now we will perform this del y on this xy square plus yz cube. So del y will operate on the y square, x as it is, and y square is 2y. Then it will operate on this y term. It gives you 1 and zq as it is plus k cap del del z over this term del del z. So in the first term there is no z, so it is 0. The second term there is z, so it gives you basically 3y square, right? It's very simple. So final result is y square. This is not the final, this is the after simplification is y square I cap plus 2xy j cap plus 2xy plus zq cap plus 3y square. So now it's your task that find out this gradient of r at the point of 1. Okay, and just you have to insert x is equal to 1, y is equal to -1, and z is equal to 1, and you will get the final something into I cap plus something into j cap plus something into, you will get the final. So the problems regarding the gradients is very simple to solve that one. So just practice more, and if you find any difficulties regarding these topics or regarding the physics, you can join uh, coaching spectral education. You can join this one, and if you want to join, you can write in the comment box. I'll provide everything. What is the process to join that coaching? So now it is a very important and very powerful problem that it is asked that find out that gradient of r to the power n, where r is a position vector x I cap plus y j cap plus z k cap. But what is this r? Is this a vector? No, this r means that the magnitude of r vector, magnitude of r vector, and you all know that magnitude of r vector is x square plus y square plus z square, or r to the power n, you can write that is x square plus y square plus z square whole to the power n 2. And when this is asked gradient of r to the power n, that means basically I cap del del x plus j cap del del y plus k cap del del z, it will be operated on x square plus y square plus z square whole to the 2. But if you go with this method, it is a lengthy process. But there is another formula, and with this formula you can solve these problems in a single line. Okay, let's say it. So how to solve? What is the formula, working formula for that? So you all know that in ordinary differentiation, ddr of r to the power n, what is its result? It is n r to the power n minus 1, right? Similarly, we'll apply the same rule here, that is a gradient of r to the power n is basically n r to the power n minus 1. But as you all know that gradient is a vector, but up to that there is no vector sense, so we have to multiply r. Okay, and if you simplify this one, gradient of r to the power n, it becomes n r to the power n minus 1, and in place of r cap we can write it is r vector by r, and if we do this is r to the power n minus 1 and r, then this together form n r to the power n minus 2 r vector. So this is the working formula, you can say, for gradient of r to the power n. So let's solve one problem. Let's say that find the gradient of r to the power 7. What will be its value? So here n is equal to 7. So simply you can find that gradient of r to the power 7 is equal to n, that means 7, r to the power n minus 2, that is 7 minus 2, and r vector. Okay, so it basically 7 r to the power 5 r vector. So just do it by yourself. What is gradient of r to the 9? Okay, and let me know in the comment box what is your result. Okay, so I think I should stop here, because otherwise this video will be very lengthy. In the next video I'll discuss about some very useful application of the concept of gradient the scalar field, and stop here. Bye bye, we'll meet again in the next video. Okay, stop here.